Thank you. Thank you for that kind introduction. So now I got a lot of expectations here. See if I can fulfill it. So I'm going to talk about the Lambda calculus. And as you said, outside computer science, it might not be that known, but if you have studied computer science, you probably know quite a lot about it. So my goal here is to give an introduction so you get a grasp of what it is. And we're also going to do some exercises, and I want you to do something, because then you actually learn something. So I'm going to first talk about the Untight Lambda calculus, that is the foundation. And we're going to do some exercises deriving some trees of Lambda terms. And then I'm going to say a little bit about types and type safety related to this. So I will have bugs in the lecture. So there will be some errors actually. And I would like you to also in the chat say when you find something. So it's a way for you to keep a little bit alert so you can, don't fall asleep, hopefully. So the Lambda calculus. What is it? Of course, it's a lambda. And what is a lambda? It's a Greek letter, right? But it's also an abstraction. An abstraction, and this is the Lambda abstraction. That contains a variable that is binding a variable inside this term. This term would be the body. And when you start to use this in a programming language, it's actually a lambda is basically an anonymous function, a function that is not given a name. So I will first start to, before going to the theory, I want you to show a little bit what does it look like in a programming language. And I will show some examples in Python, not because I particularly like Python. I mean, it's in a fine language, but I think for this audience, this might be the language that most people are familiar with. So we have here a lambda. So this is how you can define a lambda in Python. And you see here, if we look the same, this looks very similar to when we looked at the lambda, the mathematical notation, that we have a lambda, we have a variable, and then this variable is within the body. This is the body, and x is bound within this body. And here in Python, we just gave this whole lambda then a name. We call it double. And since this is a function given a name, we can call that function lambda and give them an argument 5 and print it out, and we get an output of 10. Okay, so you can in Python also define, of course, a function like this. So what's the point of making it anonymous? Well, you can use it in many different ways, and this is particularly in functional programming, but we'll see also that many other standard programming languages start to use these kind of abstractions, and more functional thoughts comes into many programming languages. So here we have an example in Python where we're using the map function here. So we have a list with a number of values or integers, and we have a map. And this map function is then taking as argument a function. And here we see that this function is a lambda, and it's anonymous. So you can supply that directly. So here you see that it is really anonymous because we haven't given it the name, and then we give the list as an argument. And then you compute, and the normal thing is that for each element, the map function is then applying this function and multiplying it by 2. So 3 times 2 is 6, 2 times 7 is 14, and so forth. Of course, this can be used in many different ways, and this is kind of just some light touch of a functional way of programming. You have a list, so here is a filter function. So it will then return all the elements that satisfies this predicate that we define here. So everything that is larger than 8 will be returned from this list. So in that case, it's 10, 33, and 85. And of course, since this lambda, we can also give this lambda a name, and then we can send that value. So a lambda is a value that can be passed around, and here we pass it to the function f. So you can actually pass it around as a function to another function. And this in programming language, we talk about high order functions, that you can pass around functions and you can create new functions. And this becomes a very powerful paradigm. So if you haven't used this when you're programming, it's something that could be very interesting. But so I just wanted to start here with the Lambda Calculus to show some practical things that you can actually use this theory for. Okay, this was the output here. So lambdas are defined in different languages. Python, this was the syntax. Haskell, which is a functional programming language with lazy evaluation. You define it like this. Scala, this is the syntax for that. C#, JavaScript, similarities you can see here. OCaml, you have a little bit different style. Standard ML, Lisp, one of the first languages that had lambdas. So you can see that you can have some different syntax. And of course, when people learn to know a programming language, syntax matters, but it's not really the same thing as the semantics, the meaning of the program. So if we take a view on here, a very brief view of the history of connected to the Lambda Calculus, we see here that we start here in the 1930s and now we see that there's more and more languages adopting a more functional style, even if there are other paradigms, but like, for example, C# have introduced it, and then many languages introduce different notions of high order functions. So Haskell was one of the key languages that are, made functional programming big. Standard ML is another one that came earlier. It was Robert Milner's group at Cambridge that worked on that, and also in Edinburgh. And they actually, ML stands for meta language. So, and they actually defined ML, this is a standard version of LML, but ML as a meta language to define this LCF, which is one of the first theorem provers. So they wanted to have a good typed language, function language, to be able to define the LCF theorem prover. Going back in history, we have Lisps, which is with McCarthy. And then we have this guy. And you can post here, who is this? It's Alonzo Church. So he's the one that basically defined the Lambda Calculus in the 1936, was one of the first papers. And he had a student, he had many famous students actually, but one student is perhaps famous so that nowadays people know who this is. And this is Alan Turing. So I guess many people, if you ask on the street, maybe they've seen the movie and they say, oh, this is the guy that did this in World War and solved this Enigma crypto, which he did. I mean, he's an amazing guy. But one thing he did, as many of you know, is the Turing machine, define the Turing machine. And so the research in the 30s here was not about, making nice abstractions here in programming languages, but rather something else. And it was about the attempt to formalize what it means about computability. So that was something that puzzled a lot of mathematicians, because these guys were mathematicians. And there were different attempts, like the Lambda Calculus by Church, the Turing machine by Turing, and then Gödel also worked on this, and had these general recursive functions. And there's something called the Church-Turing thesis that they worked together, or actually they did this in different papers, that they proved the equivalence of all these. So that means that we often say that it's Turing complete, that it's computable, like you can compute on a computer. And the Lambda Calculus is also Turing complete. And you'll see that Lambda Calculus is a very, very small calculus. So these were the main purposes at that time. And it's kind of interesting that he was the PhD student. I haven't really figured this out, but Alan Turing got his PhD in 1938. And it said that the Turing machine was independently developed by him and Alonzo Church. So they were not collaborating on that. I'm not sure actually if Turing did his PhD in 2 years, or if they were not speaking very much as a PhD student. But it's not impossible that he did it in 2 years. I haven't really figured this out. But it's interesting. It's really, a lot of things were happening in the 30s. What we can also say about the Lambda Calculus is that it's really the foundation one of the foundation, but I would say one of the major foundation building blocks for modern programming language research today that is used in various settings. Okay, so let's look at some syntax and semantics. So what do we mean here? When we talk about the language, we often talk about syntax and semantics. So syntax defines the structure of how you handle symbols in a language. And typically you define it with a grammar, the concrete syntax, the grammar, and then you have a parser, you have a lexing and parsing and so forth. That defines the syntax of the language. But often researchers are more concerned with the semantics, the meaning of the programming language. And you can also formalize that. And we will actually do some formalization today on the semantics of the Lambda calculus. So you saw here, there were different ways of writing these lambdas here. So this is concrete syntax in different languages. But often when we want to talk about semantics and connect that to syntax, we do not use concrete syntax. We use something called abstract syntax, where we remove things that are not so important, like is it called lambda or a slash, where do we have parentheses and so forth. Instead, we have an abstract syntax. And you can define the abstract syntax language formally using Backus norm format, BNF, which is the typical case. And this is the syntax, the abstract syntax definition of the Lambda calculus. So what we see here is that we have it's called a non-terminal to the left here. And then we have different terminals, and these are different productions. So here we have a free variable or a variable that can be free or bound. Here we have the Lambda abstraction that is bounding. So this variable here is binding the variable inside the term t here. And we often say terms. Sometimes we use the term expressions. It's the same thing. Often when you define this, so some authors use e here instead. And then you have an application. So application is if you have a function and you apply some argument to it, so that you can compute the result. So this is the whole syntax of the Lambda calculus. But we haven't talked about the semantics yet. So what is it concretely? Well, I mean, we will have this notation when we reason about it more mathematically. If you would implement it in a functional language, you can implement it using variant types here, data types. So this is in OCaml, for example, where you then have a variable, could be represented as a string, typically have other representation from efficiency. Lambda would be the name and the term. So you see here the recursion here, term, recursion back to term here. So there's a recursive definition. It's the same thing here. T refers to this T, which can be any of these ones. And they have an application. So this is the Backus norm format. And often if you read papers, research papers, you typically see this as the definition of the abstract syntax. But it's actually another mathematical notation that is beneath here. So what we are actually assuming here is that it is an inductive definition on sets. So suppose that we have V here, that is a countable set of variable names. And then we define the set of terms, so all possible terms, as a smaller set T, big T, such that if we have a V, a variable here, X, then that X is also a term. So this is basically what we implicitly do with this Backus norm format here. X is a T. If T is a term and X is a variable, then this expression is a term. So then we are inductively defining this set, saying that this is a term. If T1 is a term and T2 is a term, then it's T1 applied to T2 a term. So this is a way of defining this as an inductively defined set. And then you can do different kinds of proofs on this, like structural inductions or well-founded inductions on this set. And this is how you prove things on these languages. So even if this is kind of assumed that this is the underlying thing, people tend to write just the BNF syntax because it's more compact and easier to write down when the calculus becomes more complicated. Okay, let's keep this one here so we have that for the future, so you can remember it when we are looking at different terms. So we have here a lambda, an expression, and you see here that the parenthesis matters here. You will see that later. So there are some conventions when we write out these abstract syntax, just abstract syntax terms, so that we get a clear meaning. So this is actually can be seen as a tree. So here you have the application node that is applying y to the lambda, and this is the lambda, and under the lambda you have the body, and the body is just an x. So this is a different way of viewing this term. Here we have another one. Here is a convention that this lambda body is reaching out to this whole thing here. So here you have a lambda, and within that you have a body with an application of x to y. So you see this is the application here. So can you have more than one parameter? It's kind of strange if you just can program with one parameter for a function. Well, what you can do, and what you typically do, is to have currying, and it's accounted by one of the famous researchers called Turing. So that is basically that you nest several lambdas, and in this way you get several parameters. So here we have two lambdas nested, and then we are applying two values to it. So A is the first argument, and B is the second argument. And this function then has two parameters. Or actually, it's a nesting of two lambdas, and that's why it becomes two parameters. And that's why it's called currying. So to show this, this is the same thing. It's just showing that you have a what actually happens with our parentheses. So the precedence here. So we see that this lambda is inside this other lambda, and then it's left associative the applications A and then B. If you show the tree of this one, it will be an app, and below you have the nested lambdas. So when you get this understanding how you read these trees, you typically never write down the trees. You can just look at the terms and see how it's connected. So if you haven't fallen asleep yet, I would like to ask you a question to see if you are awake. So which variables are bound by a lambda? So if you look at this term here, which lambda, which variables are bound by a lambda here? Think about that for about 15 seconds, and then I'll give you the answer. Okay. So only x is bound here. So you see x here is bound by this lambda. Y is actually not binding anything. A is free and B is free. So now you wonder, what do we mean by free? So let's define what we mean by free variables. So this is a definition of free variables. It's defined as a recursive function. So we have here free variables, and it's defined by these three equations. So free variables, if the term that you send into this function is x, you return the singleton set x. If what you get in here is a lambda, then the free variable is the set is the free variables set of free variables of t1, this one, and then you remove x from that one. So it's that because x is binding, so it's not free anymore. And then you have the free variables of an application t1 and t2, and that's the intersection of free variables t1 and free variables of T2. Okay. Are you asleep? Are you awake? It's a bug. That cannot be true, right? It cannot be the intersection of free variables there. These are two terms, applications, and then you want to have the free variables of both these ones. So it should be a union. I hope you see it now. It's better when it's physical, because then you can actually see when people are sleeping. Now it's kind of hard if you don't have their camera on. Okay, so let's look at some more examples. Question: which variables are bound and which are free in the following, and which lambda is actually binding what variable? So this one is the first question. So question 1, which variable is bound and which is free? So just look at that for a little while. Okay, so let's see if you get the right answer. So just to see here, as you know, that we have a parenthesis around this. So X is bound, right, of that one, and Y is free. Okay. Question number 2. Which variables are free and which ones are bound here? Take a look at that. And it might be hard to follow because it goes fast, but when you have an answer, post it, so then I can at least see if someone can see it. Yeah, so X and Y are bound, right? And Z is free, but which one is binding this X? Well, you see there we have a lambda there and a lambda there, and it's the closest one that is binding. Right? So this lambda is binding this X. This lambda is actually not binding anything right now, and nothing is binding Z. So I hope you get the key of this. Okay. Alpha conversion and beta conversion. So we want to give the lambda calculus some semantics, right? Some meaning. So what do we have here? We have a reducible expression, often called a regex. So that means that is a term that can be reduced. And here, if you see here, this is a lambda, it's a function applied to some argument, so we can reduce it. Then it's regex. So now I'll show you some of the fundamental equations that are defining the lambda calculus. And the first one is the beta conversion, or the beta reduction rules when you go in one direction, but it's actually an equation, so you can go in the opposite direction. What does it say? Well, it says that we have here a lambda and a term, and this is the same thing as we take and substitute T2, this one, for all free variables of X inside T1. And if you think about it, when you're applying a function, this is really what you do. You apply a function and you replace all the terms, these T2, you replace the X that occurs inside here with what is the argument. And we write it like this. There are some different notations how to write this. But this is the substitution. That's called the beta conversion. So let's define what we mean by substitution. If we substitute, and now again, we will go through all the different syntactic forms here. So we have here a substitution of, we have a substitution of something that is an X, and this X is the same one. So then it will be substituted. We are replacing X with this, and then we get T1. Which other forms do we have? We have we have another variable. If so, here x was equal to x, it's the same x, right? But if we have y, and there we have x and y are not the same, nothing should be changed, right? Then we should keep y. If we have here a lambda, now it's getting a little bit more complicated. If we have a lambda here, if we are substituting x here and we have y here, so we're substituting into a lambda, then this substitution, goes inside the lambda here. So it's put inside the lambda. Is it correct now? Not yet. Well, we need to say that x and y are not the same, because if they were the same, it will stop, because then that one would bind that, and then the variable would not be free, and we don't have to go any further. And it's actually one more thing. And if you see this directly, either you are extremely clever or you have studied the Lambda Calculus before. So there is one constraint using this notation of free variables, and that is this, that y, so y here, must not be a free variable within this term that is substituted. Y cannot be, so the free variables of the body, of the thing that is substituted, cannot be in y. And why is that? Well, that is called capturing. So then it will be actually captured, the substitution. So the second rule, which could be presented before because the alpha and this was the beta, but it makes more sense to show it in this order, is what's called alpha conversion. And it basically means that if you have some names and they are in a lambda and they are binding some variables, you're free to change the names, as long as you're just changing the names that are bounding, because what the actual name is doesn't matter, but you're still allowed to change it, and that is called alpha conversion. So you cannot rename free variables, but only the bound ones. And often when people do pen and paper proofs, they say that this is true up to the renaming of bound variables, and this is sometimes called the Behrendrecht's convention. This is not that easy to do in a automatic theorem proof. Then you have to have other representations. So this is how you handle it, because you can always then just change the names using alpha conversion, and then the substitution goes through. Finally, we have the application here, T2 and T3, and that is simply that you substitute in both. Okay, so that's about the alpha conversion and beta conversion. We have one more that was also in Church's original paper, and that's called Eta Conversion. And that is, if the term is a function, is a lambda, then you can expand it. So if you have an f, you can wrap a lambda around it and then put an application to it, and it's the same meaning. Right. So if this is a function, you can apply. So it doesn't give, and sometimes we talk about the eta expansion for that reason. So is this it? Is this everything in the Lambda Calculus? Yeah, basically these are the rules, and that you can compute anything. So all machine learning algorithms, everything you can actually encode in this Lambda Calculus. You can use something called Church numbers to find integers, tuples, everything with just these constructs. Don't do it, because the computation becomes extremely slow. So in one of my courses, people have to do this for the factorial function, which goes pretty slow when you compute it, but you can do it. But there's more to it. So this is one, it's the book by Behrendrecht. So I probably pronounced it incorrectly since he's Dutch, I think. But the Lambda Calculus, it's a book about 600 pages about just the semantics and the definition of the Lambda Calculus. So that means that you can say quite a lot about it. You can make many interesting proofs and do many things with it, just the Lambda Calculus. Another book here that I strongly recommend, this one I might be a little bit, it's not like a page turner. This one, on the other hand, is a really, really good book in programming language theory. It's kind of the Bible in programming language theory, types and programming languages. And this is actually my copy that I had since my PhD, and it's kind of broken, so it's been read many times. Okay, so you can have, when you're evaluating terms, you have a term, and we will work on one example here. So here you see that you have a lambda, and you have several other lambdas. So then the question, which redexes are possible here? What can you reduce? Well, we can see here that we can probably apply this lambda to this lambda, substitute that. We can also take this whole thing here and apply that to this lambda, replacing x. So you see that there are several possible redexes in the same expression. So then there are different evaluation orders. And one is called by value, that you reduce first right side and then to a value. So in this case, if you look from outside, you have this function, and then you have one big argument. And that means that this must be reduced to a value, and a lambda is a value, but the application is not a value. So if you reduce that, you see that we substitute this lambda function here into y, and then we remove this lambda, and then you just have the lambda with z left. And then you can reduce the next one, so you substitute that, and then you get y and the lambda z. So this will be an evaluation strategy for call by value. This is actually the evaluation strategy that is most common in most programming languages without knowing it. This is the case. It's for example, in Java, C, C++, OCaml, etc. And here is, if you remove the parentheses, this is the expression. Another one is called by name. Then you substitute the leftmost with the outermost directly. So here you see, you take this whole expression, you don't evaluate this, but you substitute, so you apply it to this function. And then this outer lambda disappears, and y becomes the outer, and x is replaced with this whole expression. And now this is a lambda, and we cannot do anything more. So anyone knows what languages that are using call by name? Haskell? Yeah, almost. I mean, it's the same. This is kind of a call by name, but it's called lazy evaluation. And the one key difference here is that when you do call by name, you can duplicate terms. So you get more computations. So they have a sharing inside here, so you don't have to recompute terms, even if you substitute. And that's called lazy evaluation. So it's almost like call by name, but avoiding recomputations. And Algol used call by name, right? I guess not so many people know about Algol anymore, but it's one of the more important if you look at the history of languages. I agree, Safe. Then you have full beta reduction, and that means that you can reduce in any regex. So here in the case, if we first do like call by name, then we can actually reduce under lambda, right? So that is full beta reduction. And you can choose to start with the call by value strategy. You can do it in any order. And that is actually what's called the Church-Russell theorem. And now people more call it confluence, means that the order that we reduce doesn't matter. You will always result in the same end term under full beta reduction. which is a very important. So this kind of confluence property is something that typically people are proving when they are performing different kinds of proofs on their systems. Okay, so let's go and do something. So now I would like you to pick up some pen and papers, and I'll see if I can stop the sharing here, and then I will try to share here. Yes. Okay, so we have now, we're going to work on a specific calculus. So we start by having the syntax, and then we define calculus. We have x here, lambda x dot t and t. So this is the abstract syntax for the lambda calculus. What we
David,
also added, yes.
David, there is a comment from Dillian.
Okay. I cannot see the.
Okay, it says, but you may diverge using one evaluation order, but terminate in another order.
Okay, Dylan, maybe we can take that afterwards right now, because I just feel that we have a little bit a short amount of time right now. So I'll continue here right now.
Okay.
Okay, so we have here also another syntactic form, the value. So here now in this calculus, we define that we have a value abstraction. Okay, so this is the syntax. What about the evaluation? Semantics. So we define this relationship here, t to t prime. So I will now define it using what's called operational semantics and small step operational semantics. And there will be different rules that we can apply that defines the meaning of this small language. So first we have then T1 and T2. So this is an application. And then it's reduced to something, but here I draw this bar, and this means that it's an inference rule. So at the bottom here, we have the conclusion, and above we have the premise. So that means that given that T1 can reduce to T1 prime from this one, we have a new term here. It's called T prime 1 T2. And we give this a name E app 1. So what this says is that it can reduce, if it can reduce the first term, we reduce the first term. So we can look at it that we start here, pattern match, and see, is this an application? Yes. Can we reduce? Yes. If so, this is the end term. This is how you can read the inference rule. So top is a premise, and below is the conclusion. Okay, so then we say the next one. We say that if V is a value, and we also have an application here, but T2 is not a value, then we can, and if we can reduce, so this is implicit that if this premise holds, then it's not a value because we can reduce it. Then we have V1, T2, T2 prime. And this is another app rule. And finally, we have the reduction rule. T V reduces to, and this should be familiar, X substituted to V T. We call this E. Apps. So here we just have a conclusion. So it's like an axiom. You could draw a bar over, but there is no premise. Okay, so this is the beta reduction, the beta reduction rule here. So now we have a small calculus. So my first question here is what kind of reduction strategy have I defined in this calculus, in this language, I should say? Can someone see that? So I talked about full beta, call by name, call by value. You can write in the chat if you. Well, it's the call by value actually. Why is it called by value? Well, we can see it here that we are reducing the second term here to a value before we can apply the reduction rule. So we need to reduce it to a value first, and then we can reduce it. In call by name, we could substitute directly without being a value. And we see here, the only thing that is a value is a lambda in this calculus. Right. Okay, so the next question is, show the derivation tree for this. Now I will do that because you don't know what a derivation tree is yet. And oops. We should show the derivation tree of this. Now I almost jumped to the conclusion directly. So what is the derivation tree? Here we have a lambda here. So we have one lambda applied to another lambda. So this is from the previous slide. Then the question is, which rule applies now? So from this rule, one of these rules should apply. And now this is defined right now as a deterministic calculus, so there's only one rule that can apply in each step. So it could be defined as non-deterministic, but this is deterministic. So then the question is, which rule should apply? Well, which rule should apply? Anyone? Can it be this one? It requires that this is a value, right? But this is not a value, it's a red X. So this one cannot apply. Can it be this one? Well, it says that it can reduce here the first term, but it cannot because it is a value already. So it cannot be this one. So it must be this one. So then we write E app 2 there. Okay. What happens now? Well, this rule says that we should take T2 here, which corresponds to this one, and put it on top. So we do that. We have lambda y, lambda z, right? Okay, and then we should reduce. So then the question is, which rule applies now? So you see, we are building with go inside the term, and then we want to apply a rule now. Now we can actually apply this one, right? So we have here, but we can, since this one is a value, and this one is a value, we can just apply this. So then we have y substitutes with lambda z, and y. We can write out the name of it here if we want to. And this one, now it becomes a little bit, what is this equal to? Well, it's equal to so this means that the conclusion here comes that we are reducing to, what are we reducing to? We are not reducing to lambda z. We are not reducing to this one because it was only this one that we were operating on. So we have to write out, let's take a new line, write out this again. Lambda x, lambda y. And this one then becomes lambda z. Okay, so we've taken now one step, and it's called small step operational semantics. So the thing is that with these are called congruence rules because you dive into the terms, and then you have the reduction rule, which is this one. And now you dived into the term, did one reduction, and goes out. And then you can do that again and again. So now we could have kept on going and reduce that. So this was step one. And step two would be to take this one, this term, and reduce that one. And now we can see it perhaps directly that we will reduce that using this. Right. And then if we would substitute that in step two, we get, if I write it out directly, oops, no, wrong. Y because we take this one and substitute it for x here. And this is now a value. Okay. I had a few more examples and I wanted to do as an exercise, but we're running out of time. So I think I will skip these ones. I can post it afterwards if there are some interest. You can also take my PhD course if you want to. Let's switch to this one instead. I have to stop sharing first. Okay. So what happens if you had if you get stuck? For example, that what you end up is not a value in the end. That is not good. And what that means actually in a programming language is that it can crash. Like in C, you can write programs that get stuck or basically do something that it's not supposed to do. So we have something that's called a definition of normal form. So a term is in normal form if no evaluation rule can be applied. So you cannot reduce anything more. And if you have a call by value semantics, you want to have a value in the end. So more formally, it doesn't exist a T prime such that you can go and do a reduction into T prime. Then you're in normal form. And we say in the call by value that the term gets stuck if it's in normal form but not a value. And that's the thing that you do not want to get. So can we figure out then how to not get stuck? That would be great, right? And that is when you have a type system. So you can have a type system and then have a type checker that can check statically at compile time if you have if it can get stuck, and then you can prove on this that it's actually always be sound. It will not be complete, but it will be sound. So there might be some terms that you can that could have been possible to run in the untyped world, but not safely in the typed world. So the process of type checking is that you have a term. You say that you have a term that has a specific type, or T belongs to type. And we talk also about well-typed terms. And it says that T is a well-typed term if there is some T such that T belongs to big T. So type checking is the process of that you have a term. A term here is actually a program. And the type checker either returns the type of the program or it returns an error. So you want to do this statically. It's called static type checking because it can give some performance in compile time. You typically want to prove termination, that the type checker always terminates, but it is conservative. However, in many languages, it's hard to do this for everything. So often there are dynamic checks to make it sound. For example, one thing is array out of bound checking. So for example, in Java, you have exceptions that is handling if you go out of bound. So it's a hard problem to check that statically. There are some languages, research languages, that do that for some cases, but not in common. Whereas Python, for example, is just dynamically typed. So it will check it at runtime, not statically. So you want to prove type soundness, and there is basically a shift in how you do this in '94, and that is called using the two theorems, progress and preservation. So this is the last part, basically, of the talk. So the progress means if you have a closed term, so closed term means that you do not have any free variables. So it's closed. And it's well typed, write it like that. Then T is a value, or there exists a T prime such that it can take a step. So progress means that either you're done, you have reached a value, or you can take another step. But you are well typed. The other lemma is preservation, which says you have a well-typed term here within a typing environment. So this is, I haven't talked about this, but it's all the types of all variables that you have in your program in the context. And you can take a step. If that is true, that it's well typed and you can take a step, then the reduced term is also well typed. And that means that you have a preservation of correctness. And these two together then forms type soundness. And this seminal paper here kind of changed the way people did this kind of proofs and shifted to operational semantics, which was a very important step. Now most people do this kind of proofs when they prove things on the Lambda Calculus. Okay, so just some takeaway points here. So the Lambda Calculus actually came out of the idea and the challenge about formalizing computability in the mathematical domain. And it was defined by Alonso Church, but then they have a lot of collaboration and work together, for example, with Turing when it comes to proving the correspondence between different approaches. But there were other important people here as well, of course, involved. If you look at functional programming, which is something that is not really new. I mean, Lisp is kind of functional programming. You have standard ML from the 70s and so on, but it's taking more and more momentum. So I expect that it actually will get even more attention. You can see that, for example, in the JavaScript community. But that has nothing to do with types. It's just the functional part. And another important impact here is really on the field of programming language theory, when people are, inventing new constructs, new things that they prove correctness on. And typically the foundation is the Lambda Calculus. And then this slowly goes into mainstream languages, hopefully. That is not always the case. Okay, thank you everyone for listening.
David, thank you so much.